Okay, sorry for being late. Um, Before I start, you have the exam next Monday, as you probably know. And again, on Monday morning, not morning, your class time, we will have a review of the exam. If you did find it useful for the first exam, then attend the second exam review as well. Wednesday we won't have a class. I won't be coming to Louisiana Tech because I have a doctor's appointment in Shreveport for my son. But fortunately, the way the syllabus was scheduled, Wednesday lecture is actually very useless. So it's it was supposed to be a mini lab, and then because I just didn't want to be just a mini lab, I usually did your in-class assignment for you. So the only thing that you've lost is me doing the in-class assignment for you. There was no new lecture, nothing, okay? Just in-class assignment and mini lab. We're gonna do the mini lab today, as you received, hopefully, my announcement. And for the in-class assignment, I'm just gonna upload it. You have the in-class assignment. Of course, you have the web work, but there isn't any new concept. Today will be the end of concept and materials for exam 2, okay? Friday will be a start of the third exam materials, which is operational amplifiers. Any questions about exam or anything? No? And I believe that I gave you access to exam 2 materials a while ago. Okay. I hate to say this, but for those of you who are just struggling to stay in the course, you will receive the exam 2 grades before the drop date, so you can have a very informed decision based on 2 exams and a lot of in-class assignments, web work, and nothing else. Okay, so if you remember the previous lecture, we talked about transient analysis. Now, we came across a very important parameter in our calculations and in our equations, which is called time constant, shown by tau. Now, before reading that definition, I'm going to do something, and then we will highlight the definition and see if it is consistent with our understanding. So let's consider the equation that we have for any voltage or current in our circuit, which is Y, for positive time. Now, if you remember the equation, it was Y0 positive, e to the negative t over tau. Do you confirm? This was the equation that we had for positive time. Now, can you tell me what is the units of time constant tau? Just seconds. It's time, right? Time constant, so it should be in seconds. So do you agree that when the units is in seconds, I can actually plug that as a value into t, right? So let's substitute t with tau, which is actually plugging some known time constant into the equation, and see what happens. Do you agree with that? I just plugged in tau into my equation. Okay, now, if you look at the exponential, it's just e to the negative 1. And if you give it to your calculator, it will give you 0.37. So I can write that y tau over y0 positive is equal to 0.37. Right? Now, what does it mean? It means that, for example, let's assume that your initial value of Y, whether it is voltage or current, is 100 volts, 100 amps, okay? What happens to the voltage across that element, or the current passing through that element that you're interested in after tau seconds? What's the value? 37, right? It has dropped from 100 to 37. Is that something that you expected from the knowledge of the plot of this kind of circuit? Look at the circuit. It had some value, initial value as 0 positive, and then it starts dropping. So after tau seconds, it will drop to 37% of its initial value. I just proved it for you. Is there anything confusing? So let's read the definition. The amount of time needed for the signal in the circuit, whether it is voltage or current, to reach, well, I shouldn't say reach because it's actually dropping, 37% of its initial value. Okay? So technically I can say that if that is 0.37 of y0 positive, what is this point? Tau. Now, question, when does this signal reaches, when does this signal reach 0? Mathematically, infinity, right? It never, but physically, there is some instant of time where it is so small that is indetectable by your measurement device. Do you agree with that? So what is that instant of time when we are talking about practical cases in practice? We usually refer to this table, okay? These are the values of exponential of -1, -2, 3, 4, and 5, calculated, very easy. So what happens here is that after tau seconds, your signal has dropped to 37% of its initial value. And after 5 times second, it has dropped to 0.7% of its initial value. For example, if your measurement device is able to detect more than 1% of the initial value, then it won't be able to detect any signal at 5 times seconds. Am I making sense to everyone? So what does it mean? It means that for all practical purposes, 5 times second for that specific circuit and that specific measurement device is considered as infinity. Because after that, nothing changes in the circuit. Your measurement device is already disabled at 5 tau second, 5 time constant, okay? Did that make sense to everyone? That's why actually, for most of the practical purposes, when we are talking about infinity, it means that enough time has passed so we are not detecting anything that can be actually considerable, okay? So everything is negligible. That was literally a question. After how many time constant a voltage across a resistor or capacitor or inductor in a circuit will drop to less than 1% of its initial value? 5 times. 5 time constant. I don't like actually this question. There is something wrong with it. I don't know if you noticed that or no.
It assumes that it decreases the constant rate.
Sorry?
It assumes that it will decrease the constant rate to 0 and have up to 5 times.
Okay, it doesn't decrease with a constant rate. The problem is that after 6 tau seconds or 7 or 9 tau seconds, this is still below 1%. So those are correct answers too. Am I making sense? Is there something in the statement of the problem that actually stops us from using them? No? It says how many time constant does it take? Does it take means that the minimum? I don't know.
It says fall to less than 1%, and that would seem like the crossing.
Okay. Anyway, I don't like the question, but I would have chosen 5 anyway. But since you agree with, since you're okay with this, then I don't have any beef with it. Huh? It was one of the exam questions in 2022. If you're asking about your coming exam, I don't know. I don't remember what's on it. I haven't looked at them. And usually I don't look at them before coming until after the review. Okay, let's review what we talked about in the previous lecture about transient analysis. If you remember, this was the circuit, one of the circuits that we analyzed for the previous lecture. So what is happening in that circuit? Before 0, you have independent sources connected to your capacitor, which means, and it's been in that position for a long time, which means your capacitor is completely charged, right? To the point where it is open circuit, because the circuit is DC, it's been in that position for a long time, nothing is changing, so it acts like an open circuit. Okay, and it's completely charged. Now, this is my first question. Do we have any initial value for the capacitor voltage, or it is 0?
0, right?
0 or non-zero?
For our calculation, non-zero.
It should be non-zero, right? Why? Because when is the initial value? 0 positive or 0 negative? They are the same, as you know why. So it's been charged up by a current source, so it shouldn't be 0. It's fully charged, right? So it's not 0. What happens if we let the circuit, let time pass enough after 5 tau, 10 tau, and the switch is open? What's going to happen inside the circuit? Sorry? It will release all of the stored energy through capacity, through the resistor, in the form of heat, in the form of thermal energy, okay? And it will completely discharge, and everything in the circuit will die out. So can you tell me what is the voltage across capacitor at infinity? 0. These are the 2 points that are important for the previous lecture. Why 0 positive is non-zero and why infinity is 0. And if you remember, we call that natural response, because the voltage across the capacitor is not due to some external independent source. It's only because of the initial value or initial energy stored in the system, stored in the capacitor or the inductor, okay? Anything wrong with the logic and physical understanding of this concept? Okay, so this is the equation that we had for the previous lecture for natural response, and this is the circuit. Important thing is that all independent sources get disconnected from L and C at t equals 0. Is it consistent with the circuit? Yeah. Now let's consider the second case. Just look at this circuit. So what's going on in the circuit at t equals 0 negative? Nothing. So can you tell me what is the initial value for the voltage across the capacitor? 0. What if your capacitor had some charges? You don't know. Like someone gives you a capacitor, okay, and you just put it in parallel with the resistor. How can you be so sure and say that the voltage across the capacitor at t equals 0 negative is 0? There is one statement in the, usually in the statement of the problem that guarantees that.
Is that how much time is that?
Yeah. Even if it had some charges stored on it sometime by someone, okay? It's been connected to that resistor for a long time. What does it mean? It's been completely discharged. It released all of its energy through that resistor. So at t equals 0 negative, it's completely empty. Okay? So what is y0 positive and y0 negative? 0. What happens in the circuit at y at t equals infinity? What's the difference with the previous lecture's case? At t equals infinity, you have something, some independent sources connected to your circuit, right? That keeps charging your capacitor until it is fully charged. And at t equals infinity, because everything has been in that position for a long time, then the capacitor will be open, but it's fully charged, okay? So exactly the opposite of the previous case. What do we call that scenario? We call it forced response. Because there isn't any definition, but I mean, you don't need it. Forced response means that any voltage or current that you measure in your circuit at positive time, it's not because of the initial condition, but it's because of the independent source that is connected to your system at positive time. So it is obvious that this guy is 0, but at infinity is non-zero, as you answered it yourself, okay? Any problem understanding these two cases? Just physical understanding of them, okay? Now, this is sort of a proof of the equation. You don't need to later just study that in depth, but I didn't want to just throw equations at you, so I'm going to cover it briefly. So at t equals 0 negative, what's happening in the circuit is that there is nothing going on. Nothing is connected to the circuit, so your initial value is 0. For the reason that you know, I hope by now, that the capacitor voltage cannot change abruptly, you can say that VC0 positive should be also 0. What happens at t equals infinity? Look at the circuit. What did I do to the capacitor? Open, right? And why am I allowed to do that? Because nothing in the circuit is changing. And what guarantees that nothing is changing? I'm considering t equals infinity. Time has been, enough time has passed. And based on a simple Ohm's law, when that is open, I can write it as RIS. Okay? Exactly the steps that I followed for the previous lecture. Now, if you remember, the next step was to solve the equation, solve the differential equation that I get for positive time. This is my circuit for positive time. You don't need to know how to solve this differential equation. But again, the shape of the function will be exponential. The only difference is that it's going to have some constant term as well. Okay? If you have any problem, if you don't like the fact that I'm giving you the answer, how can you make sure that this is a correct answer? No, before that. No, before that. Plug that into there and see if that makes it work, right? If you plug this VCT into that differential equation and it holds, it means that I'm correct. Otherwise, I'm not. Okay, now, what's the difference between this plot and the plot of the previous lecture? Let's plug t equal to 0. What happens? The exponential becomes 1, right? And what is VCT at 0? 0, because it will be Ri minus Ri. So it starts at 0. Is that consistent with our understanding of the force response? Y0 is 0, so it starts at 0. What happens at infinity? What happens to the exponential at infinity? It goes to 0. E to the negative infinity is 0. So the second term disappears, and you will reach a final value. Is that, again, consistent with our understanding of the force response? Yes. If you look at the plot, see how it is exactly opposite of the natural response? It will start from 0, and it will reach some final value. It will be steady at that value. Okay? Now, this is called forced response, and this is the set of equation that actually works for that. Okay? Now I'm going to write something here, very important, very, very important. Don't memorize this. Can someone tell me why?
It's too simple.
It's not always right.
More ideas? Any other opinion on this?
This application got produced, is memorized. So memorize again once I do.
Sort of, yeah. So let me get to that point. So this is force response, right? And this guy here is natural response. Are these the only two possible cases or no?
Probably not, because you're asking.
Sorry?
Probably not, because you're asking.
Okay, then give me the example.
There could be some in between.
You could have independent sources connected to the circuit before zero and some independent sources connected to the circuit after zero. So neither y0 positive nor y infinity are zero, okay? So it means it's a combination of them. Fortunately, because everything is linear, the equation is linear, the circuit is linear. I mean, this is inside the parentheses for just your general knowledge. We can apply superposition and then say that for whatever circuit that we have, the total response is going to be natural response plus forced response. So technically, I should add the two equations that I have, two sets of equations that I have for natural response and forced response together. And I will get this blue things. Does it ring a bell? Have you seen that before? That's the set of equations that I asked you to memorize in the previous lecture. Okay? Now, it's for total response. Does it work for forced response? Yes. Because if you set y0 equal to 0, then it will give you an exact equation of forced response. Does it give you the equation for natural response? Yes. Set y infinity equal to 0, and it will give you that. So this is the summary of my line argument today. This is the only set of equations that you need for transient response. Usually, I mean, let me put it this way. You get rarely any mention of forced and natural responses in your equations. So this is the equation that you usually get. A circuit is given to you, and they ask you for the voltage across a resistor, a capacitor, inductor, or a current. Okay? They never say anything about forced or natural. Which one should you go after? You should go for total. Okay? Always, we are interested in total response. And this is the equation that works for every time. Was that clear enough for everyone? Okay? This is the equation that you need. Now, do you remember that I added one extra step that wasn't actually necessary in the previous lecture? Calculation of y at infinity. I told you several times that we didn't need to do it in the previous lecture, but we did it anyway to prepare for today. If you remember, y infinity was always 0 in previous lecture. Okay, enough talking, let's do an example and see what happens here. The steps, everything that I mentioned previous lecture, exactly the same. The only difference is that for most of the step, you get non-zero values. Okay? Now I'm going to start from here, Ethan. The first step, what is the first step?
I element 0. So turn the inductor into a short.
First, step 1, analyze the circuit at 0 negative. Okay, tell me what to do to the circuit.
Turn the inductor into a short.
Yes, the inductor has been in this position for a long time, so I turn it to short. What else? The switch should be at A, right? So it should be open. What else?
20 ohm gets shorted out.
First, change the labels.
Alright, that's gonna be 2 amps.
IL0 negative and V0 negative. Now, next, what do I need to calculate in this circuit?
I'll pass this one.
Cage? I need to calculate the two things that the question is asking, V and IL. So, next, William, what is IL?
That would be 0 because we'll not notice. Can't you combine those current sources?
At which node they are combining? Okay, Jonathan.
That would be 2 amps.
Why?
It's at the least resistance.
Okay, so the first thing that you do is that I short out this 20 ohm because it's in parallel with a short circuit. Okay? So look at the 2 amps. The only path that it has is through the inductor. So that is equal to 2 amps. How about next? Pass. Cannon. Ross. What is V0 negative? Perfect. Ohm's law, right? 15 volts. One thing that I want you to notice is that the big loop and the small loop, they are actually isolated. They only share ground, but they're not connected in any other node. That's why they are completely acting independently. Do you see that? All the currents of 3 amps is going through 5, and all the 2 is going through that part of the circuit. So they are completely separate.
So when it, sorry, this is not, so when it's like going around the smaller circuit, going around, it passes the VI and it goes to ground. It doesn't feel the need to go to that or anything. Well, I'll just go to ground instead.
Well, the thing is, the 2 amps that is coming here, and then here, and then the 3 amp, they combine for a very small part of the circuit here. What is the current passing that direction? 5 amps. But it's not affecting any part of the circuit, right? Okay, so that's the first step. Step 2, T equals 0 positive. Who's next? Samuel. What should I do first on the circuit? First the switch, okay? So I'm going to connect these two. Next. Replace the inductor with current source. What's the value of the current source? Where did you get that? That was the value at t equals 0 negative. Why can you claim that the value of the current is equal to t equals 0 negative? We are at t equals 0 positive. Why can you say these two are equal? That's a very fundamental point. The inductor current cannot change abruptly. Whatever value it had at t equals 0 negative, it's going to have the same one as 0 positive, and it's equal to, was it 2 amps? 2 amps. Okay, I also need to change this label, make it V0 positive. So what is V0 positive? Next. Christopher. 10 volts? 15, you said? Braylon, did you want to try more, or you're passing? No.
It'd be some combination of the 2 amps and the 3 amps going through.
No. Next. What was your name?
Jacob.
Jacob, yeah.
Would it be the same as before?
No. Yes.
Would it get shorter?
No. Okay. Volunteer. Yes.
So would some of the 3 amps move up and then it would just go through the 20 circuit, the 5 and 20 are parallel because the 2 amp stays in the inductor?
Okay.
So it'd be 100 divided by 4. Would be the equivalent resistance? Would be, no.
You are 90% of the way. Push a little more. So let me polish what he said. First of all, do you agree that I just ignored this guy and this guy from my circuit analysis? Throw them away. Open them and throw them away. If you agree with that, why? Okay, do you remember source combination? I really doubt it, but source combination mentions that you can combine parallel current sources. One of them is going up 2 amps, one of them is going down 2 amps. Combine them, it will be 0. 0 amps means open circuit, so throw them away. They're not doing anything. Well, they're just sort of doing whatever they're doing to each other, not related to any other part of the circuit. So what we're left with is the middle part of the circuit. Now, as you were saying, the 3 amp is, some of that will go through the 20 and some of that will go through the 5. What do we call that concept? Current division. Just write a current division. Current division together with Ohm's law, of course. So first, let's write the current division. 3 amps multiplied by 20 ohm divided by 20 ohm plus 5 ohms. That will give you the current that passes through the 5 ohm, and then multiplied by 5, and it will give you the voltage, which is 12. Yes. 12 volts. Okay? What is a step 3? Analyze the circuit at infinity, right? The step that wasn't required previous lecture, but definitely you need to consider it here. Can someone give me a reason why we need to consider t equals infinity and calculate the values at that.
Because it's part of the process, part of the equation.
Yes, but how come in the previous lecture it wasn't necessary? Yes.
There's only one.
Because there weren't multiple different sources of current. It's still a little bit off to my left of these. So it goes to 0, and then 0 is just 9.
So yes, you're correct. Let me rephrase my question. At t equals infinity, or for any positive time for that matter, is there any source connected to your inductor? Yeah. So can you just say that everything is 0 at infinity? No, because there are sources connected. The reason we could do it in the previous lecture was that all the sources were disconnected at t equals 0. Not the case here. Okay, at infinity, your circuit is still here. Changing the labels. And what happens to the inductor and why? Alina, it was your turn. What happens to the inductor at t equals infinity? Sorry, I caught you off guard. And why? Jonah. What happens to the inductor at t equals infinity? Remember, infinity actually translates into everything, whatever the hell he wanted to do with himself is done with it. It is a steady state. So what happens to an inductor in a steady state, aka DC? Shorted, right? So you replace it with a short circuit. And changing this label to IL infinity, and then we need to calculate two values. So, Luini, look, whatever you want, just move to the next step. Current's 2 amps. Why? Hannah, do you agree with him? Do you agree with him?
5 amps.
Why 5 amps?
Because the 5 amps one was short.
Okay. Do you see that the 5 ohms and 20 ohms are in parallel? And all in parallel with a short circuit? So do you see that both of them are shorted out? So what current goes through them? Nothing. So the 5 and 3 will combine at that intersection point and all will go through the inductor. Right? I don't like the look on some of your faces. If you have any problem, let me know. Is there anything confusing? Just the geometry of the circuit, if it is confusing, just redraw it. Okay? Do you want me to redraw the circuit using a very simple geometry, or it is too obvious for everyone? No? Do you want me? Okay. Two amps. 3 amps. Right? I got rid of the resistors, they have no role to play. So what is IL infinity? Now, since you already confirmed that there isn't any current passing through the 5 ohm resistor, can you tell me what is V infinity? 0. Because there isn't any current passing through, and that Ohm's law will give you 0. Any problem with the third step? What was the fourth step?
Find the equation for all times.
No.
So find tau.
Time constant, right? Tau. But before finding tau, we need to find equivalent resistance. So remember, the circuit should be considered for positive time, so the switch should be at the right position. I remove all the labels because I don't need them. I also remove the inductor. Why? Because we want to look at the circuit from the terminal that the inductor is connected to, but the inductor itself doesn't play any role in the equivalent resistance. So this is basically what we want, Req. What was the other name for Req? The Thevenin resistance, right? So how do you calculate it? What's the first step in that? Kill the independent sources. Open them. So what is Req? 5 ohms in parallel with 20 ohms, which is 4 ohms. So your tau is L equivalent over R equivalent. Was it C or R? L. Oh, okay. L. Okay. What's the value of L? I don't remember. 100 millihenry divided by 4 ohms, which is 25 milliseconds. And if you remember, just for ease of calculation for the next step, I calculate 1 over tau as well. And since your tau is in milli, 1 over 25 milli is 1,000 over 25, right? (1,000 over 25 second, which is 40 second inverse. That is your 1 over tau. What is a step 5? What is a step 5? Plug in into which equation? Total response, okay? Only total response. Okay, we have two variables that we need to find. One of them is V, the other one is IL. And we refer to them as Y in my generic equation. So let's start with IL. Tell me the values. What is IL0 negative? 2 amps. What is IL0 positive? 2 amps. What is IL infinity? 5 amps. This should be multiplied by e to the negative 40t plus 5 amps plus y infinity. Simplify this. 2 amps, negative 3 e to the negative 40t plus 5 amps. That is 4t negative, and that is 4t positive. I'm just plugging in, right? All the values that you've calculated throughout the 4 previous steps. How about VT? What is the voltage at 0 negative? 15 volts. What is the value at 0 positive? Minus, what is the voltage at infinity? The exponential is exactly the same, plus 0. Simplify this. 15 volts, 12e to the negative 40t volts, that is for negative time, and that is for positive time. If you had another part added to this equation, to this question, they were asking find the voltage across the resistor at t equals 5 seconds. You have to follow all these steps so far. You add one extra step, and that is plugging 5 into this equation. That will give you the value at t equals 5 seconds. Okay? This is usually how you get it in web work and on exam. So in the last equation, in the last question, they don't ask you to write the general equation of V or IL. They just ask you to find the values of them at specific instant of time. Okay? And mini lab. Any question?